Rational functions. Our objective is to graph rational functions, as well as transform rational functions by changing parameters. Why learn this? Rational functions can be used to model the cost per person for group events such as a band trip to a bowl game. Let's look at our function here. We have f of x equals a divided by x minus h plus k. The absolute value of a is going to be your vertical stretch or compression factor. If a is less than 0, it's just reflected across the x-axis. So if you have a negative, it's reflected across the x-axis. Now for h and k. H is the horizontal translation. Left for h is less than 0 and right for h is greater than 0. Notice it's in the form x minus h. Just like all the other times we talked about translations, you have that x minus something. Well, it's going to still be in that same form. We have x minus h. And then your k is your vertical translation. So if k is larger than 0, it's going to go up. If k is smaller than 0, it's going to go down. Let's practice. So we're going to use the graph of f of x equals 1 over x as a guide. And then we're going to describe the transformation and graph each function. So for a, we have g of x equals 1 divided by x minus 3. We don't have any k. All we have is an h. And it's a positive h, so therefore it's going to move to the right 3. So this blue is your original, and the red is your g of x. So it's moved to the right 1, 2, 3. Now let's try b. 1 over x minus 2. This one just has a k value, and it's minus 2, so that means it's going to shift down 2. So it's going to be translated down 2, which it has. Rational functions. For the rational function of the form f of x equals a divided by x minus h plus k, the graph is a hyperbola. There is a vertical asymptote at the line x equals h. Remember that asymptote is one of those lines where the graph isn't going to cross it. It's just going to get closer and closer and closer to it, but it's never going to actually cross that line. And the domain in that case will be for all x values such that x can't equal h. There is a horizontal asymptote at the line y equals k. So that would mean that the range is going to be y such that y can't be equal to k. So there's no graph that can go through k. No graph that can go through h. Let's practice. Okay. So we're going to identify the asymptotes, domain, and range of the function g of x equals 1 over x plus 2 plus 4. So this is your hint below. So it's showing you that, hey, we have to make sure it's in the form of a subtraction problem on the bottom. So it's x minus negative 2, because that's the same as saying x plus 2. And then we have our plus 4 for k. So our h is negative 2 and our k is 4. So now that we've broken down our information, we can now look at our vertical asymptote, horizontal asymptote, domain, and range. So your vertical asymptote, if we recall back, your vertical asymptote deals with h. So h is at negative 2. So you're going to have a vertical asymptote at negative 2. Which means your domain is going to be all x values such that x cannot equal negative 2. Now let's look at the horizontal asymptote. That dealt with k. So you have y equals 4. So y cannot equal 4. Recall, a continuous function is a function whose graph has no gaps or breaks. The functions you have studied before this, including linear, quadratic, polynomial, exponential, and logarithmic functions, are continuous functions. A discontinuous function is a function whose graph has one or more gaps or breaks. Zeros and vertical asymptotes. If f of x equals p of x over q of x, where p and q are polynomial functions in standard form with no common factors other than 1, meaning the fraction is completely reduced, then the function f has zeros at each real value of x, for which p of x equals 0, and a vertical asymptote at each real value of x, for which q of x equals 0. Let's practice. We're going to identify the zeros and vertical asymptotes of f of x equals x squared minus 2x minus 3, and then we're going to graph. So let's start by factoring our numerator here. We need x, and then we need two numbers that multiply to give us negative 3, but when we add them, they give us negative 2. So it would be negative 3 and negative 1. And there's nothing we can do with our denominator, so we rewrite that. So now we need to find our zeros, and we need to find our vertical asymptote. Okay, so just as the previous slide had stated, our zeros are going to be when our numerator here equals 0. So for all real numbers, that would be 3 and 1. Take that negative 1, since I forgot a sign here. You need a positive 1 here so that way you get negative 2. Sorry about that. And now we have our vertical asymptote. So our vertical asymptote, we have x minus 2 here. So that's when our denominator is 0. So that would be 2. Or you can state it so that way it's actually a line, or an equation for a line. So we have x equals 2. So now to graph, you start drawing some of that information in. So you're going to have a vertical asymptote at 2, which will be right in here. So you know that your graph can't cross that line. And then you also now have your zeros. You can plot those as well. So as you can see, we have our plotted zeros, but we still don't have our graph. We may want to make a table to complete the graph. So these are some arbitrary values of x that you can plug in and get some numbers. So take a moment, pause the video, and find your y values and plot them on your graph. And when you return, all will be revealed. And there you have it. So now let's look at horizontal asymptotes. We have let f of x equal p of x over q of x, where p and q are polynomial functions in standard form with no common factors other than 1. Sounds familiar. The graph of f has at most one horizontal asymptote. If degree of p is greater than the degree of q, there is no horizontal asymptote. If the degree of p is less than the degree of q, the horizontal asymptote is at the line y equals 0. If the degree of p equals the degree of q, then the horizontal asymptote is the line where you have y equals whatever your leading coefficient of p is divided by your leading coefficient of q. This might sound a little complex, so let's try a few. So we're going to identify the zeros and asymptote of each function. Alright, so our zeros are going to be when we factor our numerator. So if we factor our numerator, we want two numbers that multiply to give us negative 6, but when we add them, we get positive 1. So that's going to be plus 3 and minus 2. So our zeros are going to be negative 3 and 2. Now, our vertical asymptote deals with this bottom right here. So when our function equals 0, or our denominator equals 0, sorry, you're going to end up with, well, x equals 0 is the only way that can work. Well, now if we look, the degree of p is greater than the degree of q. So therefore, there is no horizontal asymptote. So now we just graph. Let's try another one. So we have x minus 1 in our numerator, and in our denominator we have x squared. So we want our zeros, our vertical asymptote, and our horizontal asymptote. So we have our zeros. It's when our numerator is going to equal 0. So, well, that's just going to be 1, since it's already as simple as we're going to get it. Now we have our vertical asymptotes, so that's when we're going to make our denominator 0. So that's when x equals 0. That's the only way that's going to work. And now we need to decide whether or not there is a horizontal asymptote. Well, we have the degree of p is less than the degree of q, so therefore you're going to have one at 0. And then you can simply graph. Let's try C. So once again, zeros, vertical asymptote, and horizontal asymptote. For this one, before we can do any of these, we need to factor both the numerator and the denominator. Take a moment right now and do so. So now that it's factored, notice how this one's a lot more complex than some of the previous ones that we've done. So we can start with our zeros. That's going to be our numerator. So we know that for our zeros, we're going to have 1 and negative 1. Now, for a vertical asymptote, notice how there are two different values that are going to make this 0. Well, that means that you're going to have two vertical asymptotes. So one is going to be at negative 2, and the other is going to be at positive 2. And now for our horizontal asymptote. This is when you have to play with our leading coefficients. So the leading coefficient of our numerator is 2, and the leading coefficient of our denominator is 1. So it's 2 divided by 1, which, well, that's 2. So therefore, your horizontal asymptote is going to be y equals 2. And now we graph. So notice how you have two vertical asymptotes and then one horizontal. This is the graph you receive. Sometimes both the numerator and the denominator of a rational function will equal 0. When this happens, the graph may have a hole. A hole is an omitted part in a graph. So if a rational function has the same factor x minus b in both the numerator and the denominator, then there's a hole in the graph at the point where x equals b. Unless the line x equals b is a vertical asymptote. Because it's a vertical asymptote, well, it already can't be there. So let's try. Graphing rational functions with holes. Okay, so we have f of x equals x squared minus 4 divided by the quantity x plus 2. So we're going to simplify this, find the hole, and then we're going to graph. Alright, so we know by looking at this function here that x cannot equal 2. Negative 2. Because that would make our denominator 0. So now we need to simplify, so we're going to factor our numerator, so that way we can figure out what exact equation it is that we're going to graph. So take a moment and do that now. So now that we've simplified it, we can graph that. So graph that, however, you're not going to be able to put any part of the line on x equals negative 2. So you're going to have a hole. So it will appear as such. So you have your line with your hole, and you have now graphed a rational function with holes. And that ends our video on rational functions.